Okay, so in this video, we want to consider other applications of the cross product to problems of areas and volumes. Now, if you remember, and before we can do so, we'll have to connect the dot product with the cross product in one other way. If you recall the previous video, we had formed the so-called scalar triple product, which was U dotted with V cross W. We want to have, or look at another relation between the dot and the cross product, which will then allow us to tackle problems of area and volume. Remember that for vectors u and v in R2 or R3, we can position the vector's initial point on the same point in space, and then look at the angle between u and v. And recall that we always take the angle to be the smaller of the two angles because you have the angle theta and its complement, and the smaller of the two angles is what we define to be the angle between vector u and vector v. And so by this choice of theta, it will always be between 0 and pi. And recall the geometric property of the dot product. If you dot these two vectors together, right, this is multiplying corresponding entries of the vectors and adding them up, there is a really nice geometric interpretation of the dot product. It is the norm of u, the length of this vector, times the norm of v, the length of this vector, times the cosine of the angle between vectors u and v. And with this equality, we will have a connection with the cross product and the angle between the two vectors. So here's the equality. So if you ask about the cross product between u and v, this is a vector, and now you can take the norm of this vector, the norm squared, and we have the following equality. This will be the norm of u squared times the norm of v squared minus the dot product between u and v squared. Now the proof of this is rather messy, but at the same time very easy. Find the cross product between u and v, find the norm of this, square this, so expand this out, see what you get. You'll have a rather nasty expression. Do the same thing with these two expressions, norm of u, norm of v, multiply the whole thing out. Dot u and v, square this, subtract, and you'll see that after you expand the left and the right hand side, both sides will be equal, and therefore the equality is valid. We're not going to do that because basically it's very messy and very simple, and there is really nothing to learn from this. And this equality as is not so interesting. What's interesting is what we can get from this if we replace u dot v by the norm of u, norm of v cos of theta. Let's see what comes out of this after we make this substitution. So norm of u squared times norm of v squared stays the same, minus, and now we make the substitution, u dot v is the norm of u times the norm of v times cos of theta. The whole expression is squared, so we can square the three terms individually. We'll have the norm of u squared times the norm of v squared minus norm of u squared, norm of v squared, cosine squared of theta. Now if you notice, both terms that we're subtracting share as a common factor norm of u, norm of v squared. So we can factor the norm of u squared and the norm of v squared. And if we do so, we are left with, well, 1 here minus cos squared. But recall from Pythagoras' theorem that we have 1 minus cos squared is simply sine squared. And now if you go back, this was the norm of u cross v squared equals the norm of u squared, the norm of v squared, sine squared. And we can now take the square root. And it's okay because the norm is a non-negative quantity, and because theta is between 0 and pi, sine will always be non-negative, so we can take the square root on both sides, and there is no need for an absolute value because every term under the square root, including sine of theta, is non-negative. And if we do so, here's our conclusion. The norm of u cross v, so if you cross the two vectors u and v, we know that u cross v is a vector that is perpendicular to both u and v, but the length of this vector is the length of u, taking the square root, is the length of u times the length of v times the sine of the angle between u and v. And look how similar this result is to the equality of the dot product. With the given picture, if you dot u and v, that's the norm of v cosine of theta. If you cross u and v and take the norm of the vector, it is the length of u, length of v, but now sine of theta. And that is the equality that we were after. With this equality, we can tackle now problems of area. So here's the first problem. Suppose we have two vectors in R3. And we position their initial points on the same point in space. So suppose that vector u looks like this. And suppose that vector v looks like this. Well, naturally we have the angle between u and v, given by, say, theta. And given two vectors in space, we can naturally construct a simple geometric figure that is a parallelogram. Position vector u now here, vector v here, and you will have a parallelogram in space, either in 2 or in 3-dimensional space. This makes sense whether the vectors u and v are in R2 or in R3. And we can ask now, what is the area of this parallelogram? Well, let's see. The area of a parallelogram, or any 2-dimensional polygon, will be the area of the base times the height, or at least something as simple as a parallelogram. Not the area, sorry, but the length of the base times the height. So it is base times height. Well, the length of the base, if we view u as the base of our parallelogram, well, the length of the base is just the length of vector u, which is norm of u. What about the height? Well, the height would be the line segment connecting the endpoint of vector v onto vector u, of course, in a perpendicular fashion. This is not the height of our parallelogram, but if you notice, we now have a right triangle. And we want the height of the triangle. We have the angle between the two segments, and we have vector v. We can now use the sine function. Sine of theta, SOHCAHTOA, the sine is the opposite of the angle, over the hypotenuse, which is the norm of vector v. So quite simply, if sine theta is h over norm of v, we can isolate h, and h is norm of v sine of theta. And now we have the height of our parallelogram. So we can replace, the height is norm of v sine of theta. And if you notice this equality, and you just look up, norm of v, norm of u, norm of v, sine of theta, that's just the same as the norm of the cross product between u and v. And there you have it. The area of the parallelogram is the norm of u cross v. Beautiful, simple result. If you have two vectors in space, whether in R2 or R3, as long as they're not parallel, they will span a parallelogram, and the area of the parallelogram is simply the norm of the cross product between u and v. And think of geometrically, why this is kind of a wild result. You have this figure, you have a parallelogram. If you cross u and v, we know that by crossing two vectors, the new vector u cross v is a vector perpendicular to both u and v. So by computing u cross v, you have a vector that sticks out of the parallelogram in a 90-degree angle, u cross v, and the length of this vector happens to be the area of the parallelogram. So that's kind of odd. To find the area of a parallelogram, we construct a vector perpendicular to the parallelogram in u cross v, and the length of this vector happens to be the area of the geometric figure. We could also look at two vectors forming a triangle, right? Naturally, instead of using u and v to build a parallelogram, we could connect simply the endpoints of the two vectors and form a triangle, but the picture is fully symmetrical, so the area of the triangle is simply 1/2 the area of the parallelogram, therefore 1/2 of the norm of u cross v. And that's it for problems of areas, either of a parallelogram spanned by two vectors or of a triangle spanned by two vectors. One question is, what if we had two vectors u and v that were in R2 with two components? Could we perhaps do simpler than having to compute the dot product? And the answer is yes. Let's consider now this special case. So, same picture, a parallelogram spanned by vectors u and v. But now assuming that the vectors only have two components. So vector u is given by u1, u2. Vector v given by v1, v2. We know that we can embed these two vectors in R3 by adding a 0z component, and then we can use the norm of the cross product as we have just previously derived. So we embed in R3, the vector u becomes the vector u1, u2, 0. We embed v in R3 as well, it becomes vector v1, v2, 0. And now we have two vectors in R3 spanning the same parallelogram, and we use our result. We will find u cross v, and then find the norm of the vector, and hopefully what will come out will be quite simple. So, u cross v, ijk, u1, u2, u3, v1, v2, v3. Whoops. u3 and v3 are 0. And this will make our life much simpler. So as we've done before, C11, we delete row 1, column 1, row 1, column 1, and we'll get 0 minus 0, that's just 0. Then we'll get C12, so the negative of deleting row 1, column 2, which is again 0 minus 0, another 0. And finally C13, this will be positive. And if you notice, we'll have the determinant of this matrix, and I will leave it in this form. So determinant of the matrix u1, u2, v1, v2. And that is the cross product between vectors u and v after we embed both vectors in R3. And now the area of our parallelogram we know is the norm of this vector. So the norm of u cross v, if you recall by Pythagoras' theorem, it is just the square root of the sum of the entries squared. So it's the root of 0 squared plus 0 squared plus this determinant squared. So all we have is the root of this determinant squared. But if you think about it, if you square something then to the square root, all you're doing is you're killing off possible negative signs. Therefore, this is the absolute value of the determinant. And I'll write ABS for absolute value of the determinant of the matrix whose first row are the coordinates of vector u, the first vector, and whose second row are the coordinates of the second vector, vector v. And this should look very familiar because we actually had proof before that for regions in the plane, the determinant of a 2 by 2 matrix gives the change in area. And you can see if you take two vectors in R2 or R3, we know that the area of the parallelogram is the norm of the cross product. But when the vectors are in R2, it's much simpler than the cross product. It happens to be the determinant of the matrix U1, U2, V1, V2 in absolute value. So it's a much simpler result than with the cross product. And that's how we can compute the area of a parallelogram or of a triangle spanned by two vectors in either R2 or R3. In R3 we have no choice, norm of the cross product, or half of this for the triangle. In R2, absolute value of the determinant for the parallelogram. 1/2 of this would be the area of the triangle spanned by U and V. One more application, and that will be to the problem of a volume. Let's start with a different page. And this is something we've said before, but we've never actually proved. Right? We've said before, if you take a region, a solid in R3, and a 3 by 3 matrix, if you multiply every point of the solid by the 3 by 3 matrix, you'll have a new solid. And the question was, by which factor will the new solid get bigger or smaller? So expand or shrink. And we said before that the change in volume is given by the determinant of the matrix in absolute value. With the help of the dot, the cross product, and orthogonal projection, we can now prove that this result is true. So suppose we have the following picture. We have three vectors, say in R3, that are not lying on the same plane. Let me draw the following picture. And imagine now, this is a so-called parallelepiped. It is the three-dimensional version of a parallelogram. And you have the other edge here. And the difference between a parallelogram and a parallelepiped is this is a three-dimensional solid. And the property is that opposite faces are parallelograms and they're equal. It's a bit crooked, but you get the gist of it. So suppose that you have vector u lying here, vector v lying, say, here, and vector w lying here. So we position the three vectors initial point onto the same point, and you can now view that these three vectors, as long as they're not lying on the same plane, will span a three-dimensional parallelogram that we call again a parallelepiped. So again, this is very natural. Two vectors in R3 or R2 span a parallelogram. Three vectors not lying on the same plane will span the three-dimensional equivalent of a parallelogram called a parallelepiped. Opposite faces are equal parallelograms. And as always, a natural question to ask now is, what is the volume of this solid spanned by these three vectors? Well, let's see. The volume will be the area of the base times the height. So the area of the base times the height Well, one of these two quantities is easy because, well, what's the base? The base is the parallelogram spanned by vectors u and v. And we have just proved that the area of a parallelogram spanned by two vectors u and v is the norm of the cross product between u and v. So we now have the area of the base, the norm of the cross product between vectors u and vector v. But we are still in need of the height of our solid. Let's just call this h. That's a bit more tricky. If you think of it, the height will be the segment connecting the endpoint of w onto the surface spanned by u and v, but of course in a perpendicular fashion. Let me draw it over here. So draw a line that is perpendicular to both vectors u and v, and you can see the height would be the length of this segment right here, right? The height of the solid is the length of this segment. And this meets the vectors u and v in a perpendicular form. The question is now, how do we find the length of this segment? Well, it is a two-step question. First, let's find a direction that is perpendicular to u and to v. Well, if you remember from our previous video, this is actually quite easy, because if you want a vector that is perpendicular to the vectors u and v, all we have to do is cross u and v. Suppose the length of the vector is this. So if you cross u and v, we know you have a vector that is perpendicular to both u and v, therefore perpendicular to the base of our solid. This is vector u cross v. But there is a problem here. All this gives us is the direction. This vector may be way too long, or maybe it's way too short, right? All this gives us is a direction that is perpendicular to both u and v, therefore the base of our parallelogram. But the length of this vector may not be the height of our solid. The question is now, how do we, from the vector w and u cross v, find a vector whose length is exactly the height of the solid? Well, if you notice, this is a 90-degree angle. And recall orthogonal projections. We want u cross v to stay the same, but what if we projected vector w in a perpendicular fashion against vector u cross v? So think of pushing vector w against vector u cross v in a perpendicular fashion. You will now get this vector, and it's exactly the projection of w onto u cross v. This is the projection vector of, well, we are projecting w against u cross v. So the projection of w onto vector u crossed with v. And now this vector will be of the right length, because it is the orthogonal projection. Therefore, the endpoint is exactly where the height of our solid ends. So now let's find this vector, and then the length of this vector will be the height of the solid. So let's compute this projection and see what comes out of it. We want the projection onto u cross v of vector w, and now recall the formula for the projection. It is w dotted with u cross v over u cross v dotted with u cross v times, this is just a scalar, times the vector u cross v. And that is the projection of w onto u cross v, right? It is the vector that we are projecting dotted with the vector we're projecting onto, divided by the vector we're projecting onto dotted with itself, times the vector we are projecting onto. And if you remember, we don't really care so much for the vector itself. We only care for the length of this vector, which is the height of our solid. And of course, the height of our solid is the length of the vector, which is the norm of the vector. Take the norm on both sides. The norm of the projection of W onto U cross V is the height of our solid, and that is the norm of this vector. Well, we can simplify quite a bit because this is just one big scalar multiple of this vector. So we know we can move a scalar multiple outside the norm and put it in absolute value. So we'll have the absolute value of W dotted with U cross V over, and here we can drop the absolute value because we have U cross V dotted with U cross V. If you remember, if you dot a vector with itself, what you have is the norm of the vector squared. So U cross V dotted with U cross V is simply the norm of U cross V squared. And this is obviously non-negative, so we don't need the absolute value. But now we've pulled all of this outside the norm, and we're left with the norm of vector U cross V. Well, we can simplify. We have the norm of U cross V on top over the norm of U cross V squared. You can cancel one of them, so cancel this with this one, and you're left with something quite simple. We are left with the absolute value of W dotted with U cross V divided by the norm of U cross V. That is the length of the projection, which we agreed was the height of our solid. And now we can replace. The volume was this times the height, and let's see what comes out now. As we've just mentioned, the volume was the norm of the cross product between U and V times the height, and we have the height right here. So you have the norm of U cross V times the absolute value of W dotted with U crossed with V over, and this is where things get interesting, over the norm of U cross V. Would you look at that? We can cancel these two, and we're left with quite simply the absolute value of W dotted with vector U crossed with vector V. And that is the scalar triple product of W, U, and V. And now, what did we say in the beginning? We said we would prove that the determinant of a 3x3 matrix gives you the volume of solids, the change in factor in the volume. Well, we know, if you recall, that the scalar triple product of three vectors is a determinant of the matrix whose rows are the coordinates of these three vectors. So let's use that. This will be simply the absolute value, I'll write ABS, of, now we use our result, the scalar triple product between W, U, and V, we know is the determinant of the matrix whose first row is given by the coordinates of W, so W1, W2, W3. Second row given by vector U, U1, U2, U3. And third row given by vector V, V1, V2, V3. And so you see that the solid, the parallelepiped, spanned by vectors U, V, and W, happens to be the determinant of the matrix where the rows are simply the three vectors in, of course, absolute value. The determinant here could be negative. Now, one thing I'll do here is I'll swap these rows as to keep the order consistent. I want U, V, and then W. And why can I do this? Well, think about it. If I swap rows of a matrix, the determinant is negated, but I have the absolute value of the determinant. So I can swap rows, and the absolute value will kill the negative signs, so there's no problem. This is the absolute value of the determinant of the matrix. I will move the second row to the first row, so U1, U2, U3. The third row in the place of the second, so V1, V2, V3. And the first row, I'll move to the bottom third row, so W1, W2, and W3. And now we have our result. And look how elegant it is. It took a bit of work to derive, but the conclusion is remarkably simple. If you have three vectors in three-dimensional space that are not lying on the same plane, you can form a parallelepiped, and the volume of this solid happens to be the absolute value of the determinant of the matrix whose first row are the coordinates of the first vector, second row, the coordinates of the second vector, and third row, the coordinates of the third vector. And there you have it. This is how you find the volume of a parallelepiped. One last observation is the following. Suppose I ask you the following question. How would you check whether or not three vectors, u, v, and w, so three vectors in R3, are lying on the same plane or not? Well, think of it. If the three vectors are lying on the same plane, this means that w is lying on the plane spanned by u and v. So if three vectors are on the same plane, you have no height to your solid, you have a flat surface, hence you have a volume of 0. So the three vectors will be on the same plane if the volume of the solid is 0, but the volume of the solid is an absolute value, the determinant of this matrix. So if you have three vectors in R3 and you want to figure out whether or not they are lying on the same plane, find this determinant. If the value is positive, you have positive volume, hence you do have a solid, hence they are not lying on the same plane. But if the determinant is 0, your volume is 0, therefore you have no solid, and all three vectors must be lying on the same plane. And as we have said earlier in the course, the absolute value of the determinant of a 3x3 matrix gives you the volume. And that's it. One really nice application, if you go back, of the cross product, the dot product in the orthogonal projection, and properties of the norm, and finally of the scalar triple product.